Welcome to Loops and Loops, your gateway to the captivating realm of physics. Physics, the foundational science that explores the laws governing the universe, reveals the intricacies of matter, energy, space, and time. Join us as we embark on an enlightening journey through the domain of physics, uncovering the mysteries of the cosmos, delving into the complexities of quantum mechanics, and exploring the forces that shape our reality. Whether you're a physics enthusiast, an inquisitive learner, or simply fascinated by the marvels of the universe, you're in for a captivating experience. So fasten your loops, brace yourself for an exploration of cosmic secrets, and let's delve into the enchanting world of physics together. For physics is the branch of science that deals with the study of matter, energy, and the interactions in the natural world. It seeks to understand the fundamental principles governing the behavior of objects, from the smallest particles to the vast expanses of the universe. In nature, there are four fundamental forces that govern the interactions between particles: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. These forces dictate the behavior of matter and the structure of the universe at both the macroscopic and microscopic levels. Classical mechanics is a foundational branch of physics that describes the motion of objects under the influence of forces. It encompasses the principles of motion developed by Isaac Newton in the 17th century, which laid the groundwork for our understanding of motion and dynamics. Newton's three laws of motion are fundamental principles that govern the behavior of objects in motion. The first law states that an object will remain at rest or in uniform motion unless acted upon by an external force. The second law relates the acceleration of an object to the force applied to it and its mass. The third law asserts that for every action, there is an equal and opposite reaction. Inertia is the tendency of an object to resist changes in its motion. It is directly related to an object's mass, with more massive objects exhibiting greater inertia. Mass is a measure of the amount of matter in an object. It is a fundamental property of matter and is measured in kilograms. Acceleration is the rate at which an object's velocity changes over time. It can be caused by the application of a force and is measured in units of meters per second squared. Momentum is a measure of the quantity of motion of an object and is the product of its mass and velocity. It is a vector quantity, meaning it has both magnitude and direction. Energy is the ability to do work or cause a change in the state of a system. It exists in various forms, including kinetic energy, potential energy, and others, and is measured in joules. Kinetic energy is the energy an object possesses due to its motion. It depends on the object's mass and velocity. Potential energy is the energy stored in an object due to its position or configuration within a force field. It depends on the object's position or condition and the forces acting upon it. Work is the transfer of energy that occurs when a force is applied to an object and causes it to move a certain distance in the direction of the force. It is measured in joules. How is the rate at which work is done or energy is transferred? It is measured in watts and is equal to the work done divided by the time taken to do the work. The law of conservation of energy states that energy cannot be created or destroyed, only transferred or transformed from one form to another. In any closed system, the total energy remains constant over time regardless of the processes occurring within the system. Mechanical energy refers to the energy possessed by an object due to its motion or position. It includes both kinetic energy, which is associated with motion, and potential energy, which is associated with the position of an object relative to its surroundings. Thermal energy is the energy associated with the random motion of particles within a substance. It arises from the kinetic energy of atoms and molecules as they move and vibrate. Temperature is a measure of the average kinetic energy of the particles. In a substance, it reflects how hot or cold a substance is and is typically measured using a thermometer in units such as degrees Celsius or Fahrenheit. Heat is the transfer of thermal energy between objects due to a temperature difference. It flows from objects at higher temperatures to those at lower temperatures until thermal equilibrium is reached. The difference between heat and temperature is that temperature is a measure of the average kinetic energy of particles in a substance, while heat is the transfer of thermal energy between objects. The first law of thermodynamics, also known as the law of conservation of energy, states that energy cannot be created or destroyed in an isolated system. Instead, it can only change forms or be transferred between objects. The second law of thermodynamics states that the total entropy of an isolated system can never decrease over time. It can only remain constant or increase. Entropy is a measure of the disorder or randomness of a system. It tends to increase over time in natural processes according to the second law of thermodynamics. Heat and work are both forms of energy transfer, but they differ in how they transfer energy. Heat is the transfer of thermal energy due to a temperature difference, while work is the transfer of energy due to a force acting through a distance. A thermodynamic process is any change in the state of a system, such as a change in temperature, pressure, or volume. It can involve the transfer of heat, the performance of work, or both. An ideal gas is a theoretical model of gas that obeys certain simplified assumptions, such as having particles with negligible volume and no intermolecular forces. Pressure is the force applied perpendicular to the surface of an object per unit area. It is typically measured in units such as pascals or atmospheres. Pascal's principle states that a change in pressure applied to an enclosed fluid is transmitted undiminished to all parts of the fluid and to the walls of its container. Buoyancy is the upward force exerted by a fluid on an object immersed in it. It is the result of the pressure difference between the top and bottom of the object and is responsible for the ability of objects to float in fluids. Archimedes' principle states that an object submerged in a fluid experiences an upward buoyant force equal to the weight of the fluid it displaces. This principle explains why objects float or sink in fluids and is crucial in understanding buoyancy and flotation. Fluid dynamics is the study of how fluids, such as liquids and gases, behave when they are in motion or at rest. It explores phenomena like flow patterns, turbulence, and the forces exerted by fluids on objects immersed in them. Viscosity is a measure of a fluid's resistance to flow. It determines how easily a fluid can flow and is influenced by factors such as temperature and molecular structure. High viscosity fluids flow slowly, while low viscosity fluids flow more easily. Surface tension is the cohesive force that holds together the molecules on the surface of a liquid. It causes liquids to form droplets and allows some insects, like water striders, to walk on water. Bernoulli's principle states that in a flowing fluid, an increase in the fluid's speed is accompanied by a decrease in pressure and vice versa. This principle explains phenomena such as lift in airfoils and the behaviour of fluids in pipes and channels. Aerodynamics is the study of how air interacts with objects moving through it, such as airplanes, cars, and projectiles. It examines factors like lift, drag, and the effects of airflow on different shapes. Lift is the force that acts perpendicular to the direction of motion of an object moving through a fluid, such as an airplane wing. It allows aircraft to overcome gravity and stay aloft. Drag is the force that opposes the motion of an object through a fluid. It is caused by friction between the object and the fluid and affects the speed and efficiency of movement. Terminal velocity is the maximum speed reached by an object falling through a fluid when the force of gravity is balanced by the force of air resistance. At terminal velocity, the object no longer accelerates and falls at a constant speed. A projectile is an object that is launched into the air and moves under the influence of gravity alone after its initial propulsion. Examples include cannonballs, bullets, and baseballs. Projectile motion refers to the curved path followed by a projectile under the influence of gravity. It is characterized by both horizontal and vertical motion, with the horizontal velocity remaining constant and the vertical velocity changing due to gravity. The range of a projectile is the horizontal distance it travels before hitting the ground. It depends on factors such as the initial velocity, launch angle, and gravitational acceleration. Circular motion is the movement of an object along a circular path. It is characterized by a constant radial distance from a fixed point and a changing velocity direction. Centripetal force is the force that acts toward the center of a circular path and keeps an object moving in a curved trajectory. It is necessary to maintain circular motion and prevent objects from moving in a straight line. Centrifugal force is the apparent outward force experienced by an object moving in a curved path. It is a result of inertia and is not a true force, but rather a perceived effect of the object's tendency to move in a straight line. Angular momentum is a measure of an object's rotational motion. It depends on both the object's mass and its rotational velocity, and it remains constant unless acted upon by an external torque. Angular momentum plays a crucial role in understanding the behavior of rotating objects, such as planets, stars, and spinning tops. Torque is the measure of the force applied to an object that causes it to rotate around an axis. It depends on the magnitude of the force and the distance from the axis of rotation. Torque is essential in understanding rotational motion and is commonly encountered in situations involving the turning of objects, such as opening a door or tightening a bolt. Rotational inertia, also known as moment of inertia, is a measure of an object's resistance to changes in its rotational motion. It depends on both the mass of the object and how this mass is distributed relative to the axis of rotation. Objects with larger rotational inertia require more torque to change their rotational motion. Newton's law of universal gravitation states that every particle in the universe attracts every other particle with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. This law explains the force of gravity between objects, such as the attraction between the Earth and the Moon or between the Sun and the planets. Gravitational force is the attractive force between two objects with mass. It is responsible for phenomena such as the Earth's gravitational pull on objects near its surface and the gravitational interactions between celestial bodies in space. Weightlessness refers to the apparent absence of weight experienced by objects or individuals in free fall or in orbit around a massive body. In reality, weightlessness occurs when the force of gravity is counteracted by the inertia of the falling or orbiting object. Escape velocity is the minimum velocity required for an object to break free from the gravitational pull of a celestial body without further propulsion. It allows objects to overcome gravity and reach space without falling back to the surface. Kepler's first law states that the orbits of planets around the Sun are elliptical, with the Sun at one of the foci of the ellipse. This law revolutionized our understanding of celestial motion and challenged the idea of perfect circular orbits. Kepler's second law, also known as the law of equal areas, states that a line segment joining a planet and the Sun sweeps out equal areas during equal intervals of time. This law describes the varying speed of planets as they orbit around the Sun. Kepler's third law, also known as the law of harmonies, states that the square of the orbital period of a planet is directly proportional to the cube of the semi-major axis of its orbit. This law provides a relationship between the orbital periods and sizes of planetary orbits. Orbital mechanics is the study of the motion of objects in space under the influence of gravitational forces. It involves analyzing orbits, trajectories, and maneuvers of spacecraft, satellites, and celestial bodies. A geostationary orbit is a circular orbit around the Earth at an altitude where the orbital period matches the rotation period of the Earth. Satellites in geostationary orbit appear stationary relative to a fixed point on the Earth's surface and are commonly used for communication and weather monitoring. Elasticity is the ability of a material to deform reversibly under the application of a force and return to its original shape when the force is removed. It is characterized by the material's stiffness, flexibility, and resilience, and plays a crucial role in various engineering applications. Stress is the force per unit area acting on a material, causing it to deform. It is a measure of the internal forces within a material and is often expressed in units of pressure. Stress can lead to strain, which is the resulting deformation or change in shape of the material under stress. Strain refers to the deformation or change in shape experienced by a material in response to an applied force or stress. It measures how much an object's dimensions change compared to its original size or shape. Young's modulus, also known as the modulus of elasticity, is a measure of a material's stiffness or resistance to deformation under tension or compression. It quantifies the ratio of stress to strain within the elastic limit of the material. The speed of light is the speed at which light travels in a vacuum. In a vacuum, light travels at a constant speed. This speed is considered one of the fundamental constants of nature. The electromagnetic spectrum encompasses all forms of electromagnetic radiation, ranging from radio waves with the longest wavelengths to gamma rays with the shortest wavelengths. It includes familiar forms of radiation such as visible light, infrared, ultraviolet, X-rays, and microwaves. A photon is a fundamental particle of light and other forms of electromagnetic radiation. It carries energy and momentum and behaves both as a particle and a wave. The photoelectric effect is the phenomenon in which electrons are emitted from a material when it absorbs electromagnetic radiation, typically in the form of photons. It played a crucial role in the development of quantum mechanics and provided evidence for the particle-like nature of light. Wave-particle duality is a fundamental concept in quantum mechanics that states that particles, such as photons and electrons, exhibit both wave-like and particle-like properties. This duality challenges classical notions of particles and waves and underscores the wave-particle nature of matter and energy. The dual nature of light refers to its ability to exhibit both wave-like and particle-like behaviours. Light can propagate as electromagnetic waves, exhibiting properties such as interference and diffraction, while also behaving as discrete particles known as photons. Electromagnetic waves are a form of energy that propagate through space as oscillating electric and magnetic fields. They include a broad spectrum of wavelengths and frequencies, ranging from radio waves to gamma rays. The Doppler effect is the change in frequency, or wavelength of a wave in relation to an observer who is moving relative to the wave source. It is commonly observed with sound waves, where it causes the pitch of a sound to change as the source and observer move relative to each other. Sound refers to mechanical waves that propagate through a medium such as air, water, or solids as variations in pressure and density. It is typically produced by vibrating objects and perceived by the human ear. A sound wave is a type of longitudinal wave that consists of compressions and rarefactions travelling through a medium. It carries energy and transmits sound information from a source to a receiver. Pitch is the perceived frequency of a sound wave and corresponds to the sensation of its highness or lowness. It depends on the frequency of the sound wave, with higher frequencies perceived as higher pitches and lower frequencies as lower pitches. Frequency refers to the number of cycles or vibrations of a wave that occur in a given time interval. It is measured in hertz, where 1 hertz corresponds to 1 cycle per second. Amplitude is the maximum displacement or distance from the equilibrium position of a wave. In the context of sound waves, it corresponds to the intensity or loudness of the sound and is proportional to the energy carried by the wave. Resonance is a phenomenon that occurs when an object vibrates at its natural frequency in response to an external force or vibration. This amplifies the vibrations, leading to a significant increase in the object's oscillations. The speed of sound refers to the rate at which sound waves travel through a medium, such as air, water, or solids. It varies depending on the properties of the medium, such as temperature and density. Longitudinal waves are waves in which the particles of the medium oscillate parallel to the direction of wave propagation, while transverse waves are waves in which the particles oscillate perpendicular to the direction of propagation. Standing waves, also known as stationary waves, are patterns of oscillation that result from the interference of two waves with the same frequency and amplitude traveling in opposite directions. They appear to be stationary because the crests and troughs remain in fixed positions. Interference occurs when two or more waves superpose to form a resultant wave. It can lead to the reinforcement constructive interference or cancellation destructive interference of wave amplitudes, depending on their phase relationship. Diffraction is the bending of waves around obstacles or through openings. It occurs when waves encounter an obstruction or aperture that is comparable in size to their wavelength, causing them to spread out and change direction. Refraction is the bending of waves as they pass from one medium to another with different densities. This bending is caused by a change in the wave's speed and occurs due to the change in its direction. Reflection is the phenomenon in which waves bounce off a surface after striking it. It occurs when waves encounter a boundary between two different media and are redirected back into the original medium. Snell's law describes the relationship between the angles of incidence and refraction for waves passing through different media. It states that the ratio of the sine of the angle of incidence to the sine of the angle of refraction is equal to the ratio of the velocities of the wave in the two media. Total internal reflection occurs when a wave traveling within a medium strikes the boundary of another medium at an angle greater than the critical angle. Instead of refracting into the second medium, the wave is completely reflected back into the original medium. The index of refraction is a measure of how much light or other waves are slowed down when passing through a medium, compared to their speed in a vacuum. It quantifies the optical density of a material and is defined as the ratio of the speed of light in a vacuum to its speed in the medium. Dispersion is the separation of waves into different frequencies or wavelengths as they pass through a medium. It occurs because the speed of a wave depends on its frequency or wavelength, leading to the spreading out of waves with different frequencies. A lens is a transparent optical device that refracts and focuses light to form an image. Lenses are commonly used in cameras, microscopes, eyeglasses, and other optical instruments. A mirror is a reflective surface that reflects light waves, forming images by reflection. Mirrors can be flat or curved and are used in various applications, including in telescopes, mirrors, and reflective surfaces. An image is a visual representation of an object formed by the reflection or refraction of light waves from the object. Images can be real or virtual, upright or inverted, and formed by mirrors or lenses, depending on the optical system. The focal length of a lens is the distance between the lens and its focal point, where parallel rays of light converge or diverge after passing through the lens. It determines how strongly the lens bends light and affects properties like magnification and image formation. Magnification refers to the ratio of the size of an image to the size of the object being observed. It indicates how much larger or smaller the image appears compared to the object and is often expressed as a fraction or a ratio. Chromatic aberration is a type of optical distortion that occurs when different wavelengths of light are refracted differently by a lens, causing them to focus at different points. This can lead to color fringing and blurring in images. Spherical aberration is another type of optical distortion caused by spherical surfaces in lenses, resulting in different parts of the lens focusing light at different distances from the lens. It can lead to blurring and decreased image quality. The electromagnetic force is one of the fundamental forces in nature that governs the interaction between electrically charged particles. It includes both the electric force, which acts between charged particles, and the magnetic force, which arises from the motion of charged particles. Electric charge is a fundamental property of matter that determines how it interacts with electric fields and other charged particles. It can be positive or negative, and like charges repel each other while opposite charges attract. Electric fields are regions of space around charged objects where electric forces are exerted on other charged particles. They represent the influence of electric charges and determine the direction and strength of the electric force. Coulomb's law describes the relationship between the electric force, the charges of two objects, and the distance between them. It states that the force between two charged particles is directly proportional to the product of their charges and inversely proportional to the square of the distance between them. Electric potential, also known as voltage, is a measure of the electric potential energy per unit charge at a point in an electric field. It represents the work done to move a charged particle from one point to another and is measured in volts. Voltage refers to the difference in electric potential between 2 points in an electric circuit. It determines the flow of electric charge between these points and is often described as the driving force behind the movement of charge. Electric current is the flow of electric charge through a conductor or circuit. It is measured in amperes and represents the rate of flow of charge past a given point in the circuit. Resistance is a measure of how much a material or device opposes the flow of electric current. It is determined by the material's conductivity and dimensions and is measured in ohms. Ohm's law states that the current flowing through a conductor is directly proportional to the voltage applied across it and inversely proportional to its resistance. Electrical power is the rate at which electric energy is converted into other forms of energy, such as heat, light, or mechanical work, in an electric circuit. It is measured in watts and is equal to the product of voltage and current. An electric circuit is a closed loop or path through which electric current can flow. It consists of electrical components such as resistors, capacitors, and inductors connected by conductive wires or other pathways. Circuits can be simple, like a flashlight, or complex, like those found in electronic devices. A battery is a device that stores chemical energy and converts it into electrical energy. It typically consists of one or more electrochemical cells that contain electrodes in an electrolyte solution. When a battery is connected to a circuit, chemical reactions occur within the cell, generating a flow of electrons and producing an electric current. A resistor is a passive electrical component that resists the flow of electric current. It is designed to have a specific resistance value, measured in ohms, which determines how much the resistor impedes the flow of current in a circuit. Resistors are commonly used to control the amount of current or voltage in a circuit and to protect other components from excessive current. A capacitor is an electronic component that stores electrical energy in an electric field. It consists of two conductive plates separated by an insulating material called a dielectric. When a voltage is applied across the plates, positive and negative charges accumulate on opposite sides, creating an electric field and storing energy. Capacitors are commonly used in electronic circuits to store and release energy, filter signals, and stabilize voltage levels. An inductor is a passive electrical component that stores energy in a magnetic field when current flows through it. It typically consists of a coil of wire wound around a core made of ferromagnetic material. When current passes through the coil, a magnetic field is generated around it, storing energy. Inductors are commonly used in electronic circuits to filter signals, store energy, and control the flow of current. Electromagnetic induction is the process of generating an electromotive force or voltage in a conductor when it is exposed to a changing magnetic field. This phenomenon is the basis for the operation of transformers, electric generators, and many other electrical devices. Faraday's law of electromagnetic induction states, that the magnitude of the induced electromotive force in a conductor is directly proportional to the rate of change of the magnetic flux passing through the conductor. In other words, the faster the magnetic field changes or the greater the area enclosed by the conductor, the larger the induced electromotive force. Lenz's law is a law of electromagnetism that states that the direction of the induced current in a conductor will be such that it opposes the change in magnetic flux that produced it. This law ensures that energy is conserved and that the induced current generates a magnetic field that opposes the original change in flux. Mutual inductance is the phenomenon where a changing current in one coil induces a voltage in a nearby coil. It occurs when the magnetic field generated by one coil passes through the turns of another coil, inducing an electromotive force in the second coil. Self-inductance is the phenomenon where a changing current in a coil induces a voltage in the same coil. It occurs when the changing magnetic field generated by the current passing through the coil induces an electromotive force in the coil itself. Alternating current is an electric current that periodically reverses direction, typically by curving. It is commonly used in household electrical systems and power distribution grids. Alternating current allows for the efficient transmission of electrical energy over long distances and is easily converted to different voltages using transformers. Direct current is an electric current that flows in one direction only. It is commonly produced by batteries and used in electronic circuits such as in computers, cell phones, and portable devices. DC provides a stable and constant source of electrical energy, but is less efficient for long-distance transmission than alternating current. An electric generator is a device that converts mechanical energy into electrical energy through electromagnetic induction. It typically consists of a rotating coil of wire and a stationary magnetic field produced by permanent magnets or electromagnets. When the armature rotates within the magnetic field, an electromotive force is induced in the coil, generating an electric current. An electromagnet is a type of magnet that is created by passing an electric current through a coil of wire. The magnetic field produced by the current causes the coil to become magnetized, creating a magnetic field around it. Electromagnets are used in a wide range of applications, including electric motors, generators, and magnetic resonance imaging machines. A transformer is a device that is used to change the voltage of an alternating current electrical circuit. It consists of two or more coils of wire called windings that are wound around a core made of ferromagnetic material. By varying the number of turns in each winding, transformers can step up or step down the voltage of an alternating current electrical signal while keeping the frequency constant. Transformers are commonly used in power distribution networks to increase the voltage for long-distance transmission and decrease it for local distribution and use. Nuclear physics is a branch of physics that focuses on the study of atomic nuclei and their interactions. It explores the properties and behaviours of atomic nuclei, which are the central regions of atoms containing protons and neutrons. Atoms are the basic building blocks of matter. They consist of a nucleus composed of protons and neutrons, surrounded by a cloud of electrons. Atoms are the smallest units of an element that retain the chemical properties of that element. The atomic nucleus is the central part of an atom, containing protons and neutrons bound together by the strong nuclear force. It accounts for most of the mass of an atom, but occupies only a tiny fraction of its volume. Protons are positively charged particles found in the nucleus of an atom. Neutrons are neutral particles also located in the nucleus. Electrons are negatively charged particles that orbit the nucleus in electron shells. Atomic number is the number of protons in the nucleus of an atom. It determines the identity of an element and its place in the periodic table. Atomic mass is the total mass of an atom, which includes the mass of protons, neutrons, and electrons. It is typically expressed in atomic mass units. Isotopes are atoms of the same element that have the same number of protons but different numbers of neutrons. This results in variations in atomic mass for the same element. Radioactive decay is the spontaneous breakdown of unstable atomic nuclei, resulting in the emission of radiation. It occurs in isotopes that have an excess of energy or an imbalance of protons and neutrons. Alpha, beta, and gamma radiation are 3 types of radioactive decay. Alpha particles are helium nuclei consisting of 2 protons and 2 neutrons. Beta particles are high-energy electrons or positrons emitted from the nucleus. Gamma rays are electromagnetic radiation of high frequency and energy. Half-life is the time it takes for half of the radioactive nuclei in a sample to decay into stable daughter nuclei. It is a characteristic property of each radioactive isotope. Nuclear fusion is a process in which 2 atomic nuclei combine to form a heavier nucleus, releasing a large amount of energy. It powers the sun and other stars and has potential applications for energy generation on Earth. Nuclear fission is the splitting of a heavy atomic nucleus into 2 or more lighter nuclei, accompanied by the release of energy. It is used in nuclear reactors to produce electricity. The mass-energy equivalence principle formulated by Albert Einstein states that mass and energy are interchangeable and equivalent according to the famous equation equals mc squared, where E is energy, m is mass, and c is the speed of light in a vacuum. The 4 fundamental forces in nature are the gravitational force, electromagnetic force, strong nuclear force, and weak nuclear force. These forces govern the interactions between particles and determine the behavior of matter on both macroscopic and microscopic scales. The strong nuclear force is one of the 4 fundamental forces in nature. It is responsible for holding together the protons and neutrons within the atomic nucleus. This force is incredibly powerful, but acts over very short distances, binding quarks together to form protons and neutrons, and then binding those nucleons together within the nucleus. The weak nuclear force is another fundamental force that governs certain types of radioactive decay and interactions involving subatomic particles. It is responsible for processes such as beta decay and neutrino absorption, which involve the transformation of one type of particle into another. Electromagnetism is the force that governs the interactions between electrically charged particles. It encompasses both electric and magnetic forces, explaining phenomena such as the attraction and repulsion of charged particles and the behavior of magnetic fields. Gravity is the force of attraction that exists between objects with mass. It is responsible for phenomena such as the Earth's gravitational pull on objects near its surface and the orbits of celestial bodies around each other. The Standard Model of Particle Physics is a theoretical framework that describes the fundamental particles and their interactions. It includes particles such as quarks, leptons, and bosons, and explains how they interact through the electromagnetic weak and strong nuclear forces. Quarks and leptons are 2 classes of elementary particles. Quarks are fundamental constituents of matter, combining to form protons and neutrons, among other particles. Leptons include particles such as electrons and neutrinos, which do not experience the strong nuclear force. The Higgs boson is a fundamental particle predicted by the Standard Model. It is associated with the Higgs field, which is thought to give mass to other particles through interactions. Its discovery at the Large Hadron Collider confirmed a key aspect of the Standard Model. The Large Hadron Collider is the world's largest and most powerful particle accelerator. Located at CERN in Switzerland, it collides protons and other particles at very high energies, allowing scientists to study the fundamental building blocks of matter and explore the laws of nature. String theory is a theoretical framework in physics that attempts to describe the fundamental particles and forces of nature in terms of one-dimensional strings, rather than point-like particles. It seeks to unify the 4 fundamental forces and explain the behavior of matter and energy at the smallest scales. Quantum mechanics is the branch of physics that describes the behavior of particles at the atomic and subatomic levels. It introduces concepts such as quantum states, superposition, and entanglement to explain phenomena that classical physics cannot. A quantum state describes the complete set of properties and characteristics of a quantum system, including its position, momentum, energy, and other observable quantities. It is represented by a mathematical function called a wave function. Superposition is a quantum mechanical principle stating that a particle can exist in multiple states simultaneously until it is measured or observed, at which point it collapses into a single definite state. Entanglement is a quantum phenomenon where the properties of two or more particles become correlated in such a way that the state of one particle instantly affects the state of the others, regardless of the distance between them. The uncertainty principle, formulated by Werner Heisenberg, states that certain pairs of physical properties, such as position and momentum, cannot be simultaneously measured with arbitrary precision. This principle arises from the wave-particle duality inherent in quantum mechanics and places fundamental limits on the predictability of quantum systems. Quantum tunneling is a phenomenon in quantum mechanics, where particles can pass through potential energy barriers, even when classical physics suggests they shouldn't be able to. Essentially, it allows particles to tunnel through barriers that would be insurmountable according to classical physics. This phenomenon is crucial in understanding processes like nuclear fusion in stars and electron tunneling in electronic devices. Quantum teleportation is a process where the quantum state of one particle can be transferred to another particle, no matter how far apart they are, without physically moving through the space in between. It involves entangling two particles and using classical communication to convey information about one particle's state to the other. While it's not teleporting objects like in science fiction, it's a fundamental concept in quantum information theory. Quantum computing is a type of computing that uses quantum bits or qubits to encode and process information. Unlike classical bits, which can only be in one of two states, 0 or 1, qubits can exist in multiple states simultaneously due to the principles of superposition and entanglement. This allows quantum computers to perform certain calculations much faster than classical computers. Quantum entanglement is a phenomenon where the quantum states of two or more particles become correlated in such a way that the state of one particle instantly affects the state of the others, regardless of the distance between them. It's a fundamental concept in quantum mechanics and has applications in quantum computing, quantum cryptography, and quantum teleportation. Building a practical quantum computer poses several challenges. One major challenge is maintaining the delicate quantum states of qubits, as they are easily disturbed by their environment in a process known as decoherence. Another challenge is scaling up quantum systems to a large number of qubits while minimizing errors in calculations, which requires overcoming technical limitations in qubit control and error correction. Decoherence is a process in quantum mechanics where the delicate quantum states of qubits become entangled with their surrounding environment, causing them to lose their quantum properties and behave classically. Decoherence is a major obstacle in building practical quantum computers, as it can destroy the delicate quantum states required for quantum computation. Quantum cryptography is a field that uses principles of quantum mechanics to secure communication channels. It exploits properties like quantum entanglement and uncertainty to create cryptographic protocols that are theoretically unbreakable. This makes quantum cryptography potentially valuable for secure communication in fields like finance, government, and defense. Some potential applications of quantum computing include optimization problems, example, logistics and supply chain management, cryptography and cybersecurity, drug discovery and molecular modeling, and simulating quantum systems. Quantum computers have the potential to revolutionize these fields by solving complex problems much faster than classical computers. Dark matter is a hypothetical form of matter that does not emit or interact with electromagnetic radiation, making it invisible and detectable only through its gravitational effects on visible matter and light. It is thought to make up about 27% of the total mass energy content of the universe and plays a crucial role in the formation and evolution of cosmic structures. Dark energy is a mysterious form of energy that is thought to permeate all of space and contribute to the accelerating expansion of the universe. It accounts for about 68% of the total mass energy content of the universe and is believed to counteract the gravitational attraction of matter, driving the universe's expansion. The Big Bang Theory is the prevailing cosmological model for the origin and evolution of the universe. It posits that the universe began as a hot, dense singularity around 13.8 billion years ago and has been expanding and cooling ever since. The theory is supported by evidence such as the cosmic microwave background radiation and the observed redshift of distant galaxies. The cosmic microwave background radiation is the remnant heat from the Big Bang that fills the universe and is detectable in all directions of the sky as microwave radiation. It provides crucial evidence for the Big Bang theory and offers insights into the early universe's conditions and evolution. In computational chemistry, key concepts and methods include molecular modelling, quantum chemistry calculations, molecular dynamics simulations, and statistical mechanics approaches. These techniques are used to study the structure, properties, and behaviour of molecules and materials, aiding in drug discovery, materials design, and understanding chemical reactions. In drug design, computational chemistry plays a vital role in predicting how potential drug molecules will interact with biological targets, such as proteins or enzymes. By simulating these interactions using computational models, researchers can identify promising drug candidates more efficiently, saving time and resources in the drug development process. Similarly, in materials science, computational chemistry is used to predict and optimize the properties of materials, such as strength, conductivity, or catalytic activity, allowing researchers to design new materials with tailored properties for various applications. Similarly, in materials science, computational chemistry is used to predict and optimize the properties of materials such as strength, conductivity, or catalytic activity, allowing researchers to design new materials with tailored properties for various applications. Quantum chemistry is a branch of chemistry that uses quantum mechanics to describe the behavior of atoms and molecules at the fundamental level. Quantum chemistry calculations involve solving the Schrödinger equation, which describes the wave function of a system, allowing researchers to predict properties such as energy levels, molecular geometries, and reaction mechanisms with high accuracy. Key concepts and methods in quantum chemistry include molecular orbital theory, which describes the distribution of electrons in molecules, density functional theory, which approximates the electron density of a system to calculate properties efficiently, and ab initio methods, which solve the Schrödinger equation without making simplifying assumptions. Quantum chemistry has numerous applications in understanding chemical bonding and reactivity. For example, it can elucidate the mechanisms of chemical reactions by calculating the energy barriers and transition states involved. Quantum chemistry also helps predict molecular properties, such as bond lengths, angles, and dipole moments, providing valuable insights into the stability and behaviour of molecules in various environments. Spectroscopy is a powerful technique used to analyse and characterise the structure of molecules by studying their interaction with electromagnetic radiation. By measuring the absorption, emission, or scattering of light at different wavelengths, spectroscopy can provide information about molecular composition, structure, and dynamics. It is widely used in chemistry and related fields, including analytical chemistry, biochemistry, and materials science, to identify substances, monitor reactions, and study molecular properties. Surface chemistry investigates the chemical processes that occur at interfaces between different phases, such as solid gas, solid liquid, or liquid gas interfaces. Understanding surface chemistry is crucial for a wide range of applications, including catalysis, corrosion prevention, and materials synthesis. By studying surface reactions and interactions, researchers can develop new materials with enhanced properties and optimize processes such as heterogeneous catalysis for industrial applications. Organometallic chemistry is the study of chemical compounds containing metal carbon bonds. These compounds play essential roles in catalysis, organic synthesis, and materials science. Organometallic complexes can catalyze a variety of chemical transformations, from hydrogenation and oxidation reactions to cross-coupling and metathesis reactions, enabling the synthesis of complex molecules with high efficiency and selectivity. Polymer chemistry finds extensive applications in both plastics and materials science. Plastics such as polyethylene, polypropylene, and polystyrene are ubiquitous in everyday life, used in a wide range of products from packaging materials to household items to automotive components. In materials science, polymers are essential for developing advanced materials with tailored properties, such as high strength, flexibility, or conductivity, for applications in aerospace, electronics, healthcare, and beyond. Solid-state chemistry focuses on the study of crystalline materials, investigating their structure, properties, and behavior in various environments. By understanding the arrangement of atoms and molecules in solids, solid-state chemists can predict and manipulate material properties, such as conductivity, magnetism, and optical behavior, leading to advances in electronics, photonics, and nanotechnology. Solid-state chemistry has numerous applications in electronics and nanotechnology. For example, the development of semiconductor materials such as silicon and gallium arsenide relies on a deep understanding of solid-state principles. Solid-state chemistry also plays a crucial role in the design and fabrication of nanomaterials, such as quantum dots, nanowires, and 2D materials for applications in sensors, energy storage, and catalysis. Supramolecular chemistry focuses on the study of non-covalent interactions between molecules, leading to the formation of complex molecular assemblies. By harnessing these interactions, supramolecular chemists can design and construct functional materials with specific properties for various applications. For example, supramolecular assemblies can be used for drug delivery systems, where drugs are encapsulated within molecular cages or nanoparticles, or for sensing applications, where molecules selectively bind to target analytes, leading to detectable changes in properties such as color or fluorescence. Photochemistry is the study of chemical reactions initiated by light. By absorbing photons, molecules can undergo photochemical reactions, leading to the formation of new chemical species or changes in molecular structure. Photochemistry has diverse applications, including photovoltaic, where light-absorbing materials convert solar energy into electricity, and photomedicine, where light-activated drugs or therapies are used for diagnostics and treatment of diseases such as cancer. For example, photodynamic therapy utilizes light-sensitive drugs that selectively accumulate in cancer cells and become toxic upon activation by light, offering a targeted approach to cancer treatment. Physical organic chemistry is a branch of chemistry that focuses on understanding the relationship between the structure of organic molecules and their reactivity. It combines principles from both organic chemistry and physical chemistry to elucidate the mechanisms of organic reactions. One key concept in physical organic chemistry is the idea of reaction intermediates, which are transient species that form during a chemical reaction and play crucial roles in determining reaction pathways and kinetics. Chemical kinetics is another important area in chemistry that deals with the rates and mechanisms of chemical reactions. by studying how reaction rates change with different conditions, such as temperature and concentration. Chemical kinetics provides insights into reaction mechanisms and reaction pathways. For example, chemical kinetics can help identify the rate-determining step in a reaction, which is the slowest step that determines the overall rate of the reaction. Thermodynamics is yet another fundamental concept in chemistry that deals with energy changes in chemical processes. Thermodynamics helps predict whether a chemical reaction will occur spontaneously under certain conditions and quantifies the amount of energy involved in the process. For instance, thermodynamics can be used to calculate the enthalpy change associated with a reaction, which indicates whether the reaction is exothermic or endothermic. In terms of applications, physical organic chemistry plays a crucial role in understanding reaction mechanisms and designing new reactions with improved selectivity and efficiency. For example, physical organic chemistry principles are used in the development of catalysts for organic synthesis, which enable the production of complex molecules under mild conditions and with high yields. Thermodynamics has widespread applications in chemical engineering and materials science. For example, thermodynamic principles are used to design chemical processes for the production of fuels, pharmaceuticals, and polymers. In materials science, thermodynamics governs phase transitions and the formation of new materials with desired properties, such as metals, ceramics, and semiconductors. The theory of relativity, proposed by Albert Einstein in the early 20th century, fundamentally changed our understanding of space, time, and gravity. It consists of two main branches: special relativity and general relativity. Special relativity, formulated in 1905, revolutionized our understanding of the relationship between space and time. It introduced the concept that the laws of physics are the same for all observers in uniform motion, and that the speed of light is constant for all observers regardless of their relative motion. General relativity, developed by Einstein in 1915, extends the principles of special relativity to include gravity. According to general relativity, gravity is not a force but rather a consequence of the curvature of space-time caused by mass and energy. The theory predicts the bending of light and the existence of phenomena such as black holes and gravitational waves. The principle of equivalence is a key concept in general relativity, stating that an observer in a uniform gravitational field cannot distinguish between gravity and acceleration. This principle forms the basis for Einstein's theory of gravity. The curvature of space-time, according to general relativity, is the geometric property that describes how objects move in the presence of gravity. Massive objects like planets and stars cause space-time to curve, which in turn influences the paths of other objects moving through that curved space-time. Gravitational waves are ripples in the fabric of space-time that propagate outward from accelerating masses. They were first proposed by Einstein in 1916 as a prediction of his general theory of relativity. Gravitational waves were directly detected for the first time in 2015 by the Laser Interferometer Gravitational Wave Observatory. Quantum mechanics is another cornerstone of modern physics, developed in the early 20th century by physicists such as Max Planck, Albert Einstein, Niels Bohr, Werner Heisenberg, and Erwin Schrödinger. It describes the behavior of particles at the smallest scales and has implications for understanding the behavior of matter and energy on atomic and subatomic levels. The key principles of quantum mechanics include wave-particle duality, which suggests that particles like electrons and photons can exhibit both wave-like and particle-like behavior depending on how they are observed or measured. This principle challenged classical notions of physics and laid the groundwork for understanding phenomena such as the photoelectric effect and electron diffraction. The Copenhagen interpretation and the many worlds interpretation are two competing interpretations of quantum mechanics, the branch of physics that deals with the behavior of particles at the smallest scales. The Copenhagen interpretation, proposed by Niels Bohr and Werner Heisenberg, in the 1920s suggests that particles exist in multiple states simultaneously until observed, at which point their wave function collapses into a single state. The many worlds interpretation, introduced by Hugh Everett III in the 1950s, posits that every possible outcome of a quantum event actually occurs in a separate parallel universe, leading to a branching or splitting of reality with each measurement. The uncertainty principle, formulated by Werner Heisenberg, states that there is a fundamental limit to the precision with which certain pairs of physical properties, such as position and momentum, can be simultaneously known. This principle arises from the wave-like nature of particles in quantum mechanics and has profound implications for our understanding of the behavior of particles at the quantum level. The Schrödinger equation, developed by Austrian physicist Erwin Schrödinger in 1925, is a fundamental equation in quantum mechanics that describes how the quantum state of a physical system changes over time. It is a partial differential equation that governs the evolution of the wave function, which represents the probability amplitude of finding a particle in a given state. The standard model of particle physics is a theoretical framework in particle physics that describes the fundamental particles and forces of nature. It encompasses three of the four fundamental forces: electromagnetism, the weak nuclear force, and the strong nuclear force, but does not include gravity. The fundamental particles described by the standard model include quarks, which are the building blocks of protons and neutrons, and leptons, which include electrons and neutrinos. These particles interact through the exchange of force-carrying particles called bosons. The four fundamental forces described by the standard model are the electromagnetic force, the weak nuclear force, the strong nuclear force, and gravity. These forces govern the interactions between particles and are mediated by the exchange of force-carrying particles. The Higgs boson is a fundamental particle predicted by the standard model and is responsible for giving other particles mass through the mechanism of electroweak symmetry breaking. Its discovery in 2012 at the Large Hadron Collider confirmed a key aspect of the standard model and helped explain the origin of mass in the universe. Supersymmetry is a proposed extension of the standard model that postulates the existence of supersymmetric partners for each known particle. These partners, known as superpartners, have different spin quantum numbers and could help address certain issues in particle physics, such as the hierarchy problem and the nature of dark matter. However, experimental evidence for supersymmetry has not yet been observed. The grand unified theory is a theoretical framework in physics that aims to unify the three fundamental forces of nature: electromagnetism, the weak nuclear force, and the strong nuclear force, into a single comprehensive theory. It proposes that these forces were once unified in the early universe, but later separated as the universe cooled and expanded. The string landscape refers to the vast number of possible configurations or vacua of string theory. These configurations correspond to different possible universes with varying physical properties, such as the number of dimensions and the types of particles present. The string landscape has implications for the multiverse hypothesis. The holographic principle is a concept in theoretical physics that suggests that all the information in a three-dimensional space can be encoded on a two-dimensional surface surrounding that space. This principle arises from certain theoretical approaches to quantum gravity and has implications for understanding the fundamental nature of space and information. Loop quantum gravity is a theoretical framework in quantum mechanics and general relativity that seeks to quantize the fabric of space-time itself. It posits that space-time is quantized into tiny, discrete units known as loops or spin networks. Loop quantum gravity aims to provide a quantum description of gravity and resolve the singularities predicted by general relativity. The multiverse hypothesis is the idea that our universe is just one of many universes that exist simultaneously. These other universes, collectively referred to as the multiverse, may have different physical laws, constants, and properties. The multiverse hypothesis arises from certain interpretations of quantum mechanics and cosmology. The anthropic principle is a philosophical principle that suggests that the observed properties of the universe, such as the values of fundamental constants, may be influenced by the requirement for the existence of observers, namely sentient beings like humans. It is often invoked to explain the apparent fine-tuning of the universe for the emergence of life. Dark matter is a mysterious form of matter that does not emit, absorb, or reflect electromagnetic radiation, making it invisible and detectable only through its gravitational effects. It is called dark because it does not interact with light and thus cannot be directly observed with telescopes or other instruments. Evidence for the existence of dark matter comes from observations of the rotation curves of galaxies, gravitational lensing effects, and the large-scale structure of the universe. These observations suggest that there is more mass in the universe than can be accounted for by visible matter alone. Some proposed candidates for dark matter particles include weakly interacting massive particles A actions and sterile neutrinos. These particles are hypothetical and have not yet been detected directly, but they are the subject of ongoing experimental searches and theoretical investigations. Dark energy is a mysterious form of energy that permeates the universe and is thought to be responsible for the observed accelerated expansion of the universe. Unlike dark matter, which attracts matter gravitationally, dark energy acts as a repulsive force, driving galaxies and other cosmic structures apart. The cosmological constant is a term introduced by Albert Einstein into his theory of general relativity to allow for a static universe. After the discovery of the expanding universe, the cosmological constant fell out of favor, but has been revived in the context of dark energy to explain the observed acceleration of the universe's expansion. The accelerating expansion of the universe refers to the observation that the rate at which galaxies are moving away from each other is increasing over time. This phenomenon was discovered through observations of distant supernovae and is attributed to the influence of dark energy, which acts as a repulsive force on cosmic scales. Cosmic inflation is a theory in cosmology that proposes a rapid exponential expansion of the early universe, occurring just moments after the Big Bang. It suggests that the universe underwent a period of extremely rapid expansion, stretching space itself and smoothing out irregularities. This theory helps explain various observed features of the universe, such as its large scale, homogeneity, and isotropy. Cosmic microwave background radiation refers to the faint glow of radiation that fills the universe, left over from the hot, dense state of the early universe. It is the oldest light in the universe, originating from a time when the universe was only about 380,000 years old. The discovery of the CMB in 1965 provided strong evidence in support of the Big Bang theory and has since been studied extensively to learn about the universe's early history. The age of the universe is the estimated time since the Big Bang event that marked the beginning of the universe expansion. Current cosmological models place the age of the universe at approximately 13.8 billion years, based on observations of the cosmic microwave background radiation, the expansion rate of the universe, and the ages of the oldest known stars and galaxies. According to current cosmological models, the fate of the universe depends on its overall density and the amount of dark energy it contains. If the density is high enough, the universe will eventually stop expanding and begin to contract in a big crunch. If the density is too low, or if dark energy dominates, the universe will continue to expand indefinitely, leading to a cold, dark, and featureless state known as the heat death or big freeze. A black hole is a region of space-time where gravity is so strong that nothing, not even light, can escape from it. Black holes form when massive stars undergo gravitational collapse at the end of their life cycles or when large amounts of matter are concentrated into a small volume. They are characterized by their extremely strong gravitational pull and the presence of an event horizon, beyond which escape is impossible. The properties of black holes include their mass, electric charge, and angular momentum, which are encapsulated in their size and shape. Black holes come in different sizes, from stellar mass black holes formed from collapsing stars to supermassive black holes found at the centers of galaxies and containing millions or billions of times the mass of the Sun. The event horizon of a black hole is the boundary beyond which nothing can escape. Not even light. It marks the point of no return for anything falling into the black hole. Once an object crosses the event horizon, it is inexorably drawn toward the black hole's singularity at its center. The singularity of a black hole is a point of infinite density and zero volume at its center, where the laws of physics as we know them break down. General relativity predicts the existence of singularities within black holes, but it also indicates that our current understanding of physics cannot fully describe what happens at the singularity. Hawking radiation is a theoretical prediction proposed by physicist Stephen Hawking in 1974. It suggests that black holes can emit radiation due to quantum effects near their event horizons, causing them to lose mass and energy over time. Hawking radiation is a result of virtual particle pairs being created near the event horizon, with one particle falling into the black hole while the other escapes as radiation. The information paradox is a theoretical puzzle that arises from the combination of quantum mechanics and general relativity in the context of black holes. It questions what happens to the information encoded in particles that fall into a black hole and whether it is lost forever or can be retrieved in some form. White holes are hypothetical regions of space-time that are the theoretical opposite of black holes. While black holes are characterized by their strong gravitational pull and inability to let anything escape, white holes would hypothetically eject matter and radiation outward without allowing anything to enter. However, white holes are purely speculative and have not been observed. A wormhole, also known as an Einstein-Rosen bridge, is a theoretical passage through space-time that could create shortcuts for long journeys across the universe. In theory, wormholes would connect two separate points in space-time, potentially allowing for rapid travel between them. However, the existence of wormholes remains speculative, and their stability and traversability are subjects of ongoing scientific research. The theory of cosmic censorship is a conjecture proposed by physicist Roger Penrose, which suggests that singularities within black holes are always hidden from external observers by an event horizon. This principle serves as a kind of cosmic censorship, preventing the naked exposure of the extreme conditions predicted by general relativity. The holographic principle is a concept in theoretical physics that suggests that all the information contained in a volume of space can be encoded on its boundary. In the context of black holes, this principle has led to the idea that the information falling into a black hole may be encoded on its event horizon rather than being lost forever. This has implications for our understanding of black hole entropy and the resolution of the black hole information paradox. The firewall paradox is a theoretical puzzle in black hole physics that challenges our understanding of the nature of event horizons. It arises from attempts to reconcile the principles of quantum mechanics with those of general relativity. According to general relativity, an observer crossing the event horizon of a black hole should not notice anything unusual. However, quantum mechanics suggests that the horizon should emit Hawking radiation, leading to a firewall of intense radiation that would incinerate anything falling into the black hole. This apparent contradiction between the smoothness of the event horizon and the existence of a firewall poses a significant challenge to current theories of black holes. The no-hair theorem is a conjecture in theoretical physics that suggests that black holes can be described by just three external properties: mass, electric charge, and angular momentum. According to this theorem, all other information about the material that formed the black hole is lost beyond the event horizon and cannot be observed from outside. The no-hair theorem has important implications for our understanding of black hole physics and the information paradox. The cosmic censorship conjecture is a hypothesis proposed by physicist Roger Penrose, which suggests that singularities within black holes are always hidden from external observers by an event horizon. This principle serves as a kind of cosmic censorship, preventing the naked exposure of the extreme conditions predicted by general relativity. If the conjecture holds true, it ensures that the singularities remain inaccessible and do not disrupt the predictability of the universe. The Penrose process is a theoretical mechanism proposed by physicist Roger Penrose for extracting energy from a rotating black hole. It involves dropping an object into a rotating black hole's ergosphere, a region of space-time where the rotational energy of the black hole can be harnessed through a process called frame dragging. The object can split into two parts, with one escaping the black hole's influence and gaining energy in the process. Cosmic strings are hypothetical one-dimensional objects predicted by some theories of cosmology. They are thought to be extremely thin and dense, stretching across the universe like cosmic threads. Cosmic strings could have formed during the early universe's phase transitions and might leave observable signatures in the large-scale structure of the cosmos. The theory of brane cosmology, also known as the brane world scenario, suggests that our universe may be a four-dimensional membrane embedded in a higher dimensional space called the bulk. According to this theory, gravity is the only force that can propagate in all dimensions, while other fundamental forces are confined to the brane. Brane cosmology offers an alternative explanation for some cosmological phenomena and may provide insights into the nature of dark energy and the origin of the universe. Extra dimensions are hypothetical spatial dimensions beyond the familiar three dimensions of length, width and height, as well as the dimension of time. In some theories of physics, such as string theory and brane cosmology, extra dimensions are postulated to exist, but remain compactified or curled up at very small scales, making them invisible to everyday observation. These extra dimensions could have profound implications for our understanding of fundamental physics and the structure of space-time. The holographic universe hypothesis is a speculative idea that suggests the entire universe may be a hologram, with all its information encoded on a lower dimensional boundary. This concept is inspired by the holographic principle, which proposes that the information content of a three-dimensional volume can be encoded on its two-dimensional surface. While still speculative, the holographic universe hypothesis offers a novel perspective on the nature of reality and the fundamental laws of physics. The landscape of string theory refers to the vast number of possible vacuum states, or islands of stable configurations, that arise in certain formulations of string theory. Each vacuum state corresponds to a possible set of physical laws and constants, potentially giving rise to a multiverse of universes with different properties. The landscape of string theory has profound implications for cosmology, suggesting that our universe may be just one among many possible configurations in a vast cosmic landscape. The ekpyrotic universe hypothesis is a cosmological model that proposes the universe underwent a cyclic process of expansion and contraction, with each cycle preceded by a big bang and followed by a big crunch. According to this theory, our universe may have originated from the collision of two higher dimensional branes in a pre-existing higher dimensional space. The ekpyrotic universe hypothesis offers an alternative explanation for the origin of the universe and the observed features of the cosmic microwave background radiation. The cyclic universe hypothesis is a cosmological model that suggests the universe undergoes an infinite series of cycles, expansion and contraction. In each cycle, the universe expands from a hot, dense state, similar to the Big Bang, to a maximum size before contracting again into a hot, dense state, similar to the Big Crunch, leading to the next cycle. The cyclic universe hypothesis offers an alternative to the traditional Big Bang model and may provide insights into the ultimate fate of the cosmos. The theory of eternal inflation is a speculative idea in cosmology that suggests that the process of inflation, which rapidly expands the universe in the early moments of its existence, can continue indefinitely in certain regions. This perpetual inflation leads to the generation of pocket universes within an ever-expanding multiverse. The theory of eternal inflation has implications for our understanding of the origin and structure of the universe, and may offer a solution to the fine-tuning problem of the cosmological constant. The concept of a parallel universe, also known as a parallel reality or alternate reality, refers to the idea that there may be other universes that exist alongside our own but with different configurations of space, time, and physical laws. In some interpretations of quantum mechanics and cosmology, parallel universes could arise from quantum fluctuations or as separate branches of reality in a multiverse. While speculative, the concept of parallel universes has captured the imagination of scientists and writers alike, inspiring countless works of fiction and scientific inquiry. Proposed mechanisms for the creation of parallel universes often stem from various interpretations of quantum mechanics and cosmology. One idea suggests that parallel universes could arise from quantum fluctuations during the early moments of the universe's existence, leading to the formation of separate branches of reality. Another possibility is the concept of a multiverse, where different regions of space-time undergo inflationary expansion, resulting in the generation of numerous universes with different properties and physical laws. White holes are related to black holes through theoretical considerations of the complete life cycle of a black hole. According to some models, a white hole could be connected to a black hole through a wormhole, forming a hypothetical Einstein-Rosen bridge that connects distant regions of spacetime. A wormhole is a speculative tunnel-like structure that connects two distant points in spacetime, potentially allowing for shortcuts through space. In theory, a wormhole could connect two separate regions of the universe or even different universes, providing a means of travel across vast cosmic distances. Properties of wormholes, if they exist, would include the formation of a tunnel-like structure with an entrance and an exit, potentially allowing for a rapid transit between two distant points in spacetime. Wormholes could be traversable or non-traversable, depending on their stability and properties. Proposed mechanisms for the creation of wormholes involve complex interactions of space-time geometry, such as the manipulation of exotic matter or the curvature of space-time itself. Some theories suggest that wormholes could arise naturally as a consequence of quantum fluctuations or as remnants of the early universe. The Alcubierre drive is a speculative concept in theoretical physics that proposes a method of faster-than-light travel by manipulating the fabric of space-time itself. The drive involves contracting space-time in front of a spacecraft and expanding it behind, effectively creating a warp bubble that allows the spacecraft to travel faster than the speed of light. Challenges associated with the Alcubierre drive include the requirement for exotic matter with negative energy density, which has never been observed in nature. The energy requirements for creating and sustaining a warp bubble are also immense, raising questions about the feasibility and practicality of such a propulsion system. Time travel is a concept that involves moving between different points in time, either forward or backward. While time travel has long been a staple of science fiction, its feasibility according to the laws of physics remains uncertain. Proposed mechanisms for time travel include the use of wormholes, closed time-like curves, and exotic matter to manipulate the fabric of space-time. However, many of these concepts are purely theoretical and face significant challenges in terms of energy requirements, stability, and causality violations. Closed time-like curves are paths through space-time that loop back on themselves, theoretically allowing for closed trajectories through time. While closed time-like curves are permitted by some solutions of general relativity, their existence raises profound questions about causality and the possibility of paradoxes. The Novikov self-consistency principle is a theoretical framework proposed by physicist Igor Novikov, which suggests that the laws of physics prevent paradoxes from occurring in scenarios involving time travel. According to this principle, any actions taken by time travelers would be consistent with the pre-existing timeline, ensuring that causality remains intact. Proposed solutions to the grandfather paradox which arises in scenarios involving time travel, include the idea that changes to the past could result in alternate timelines or parallel universes, where the original timeline remains unaffected. Other solutions involve the notion of a single self-consistent timeline, where time travelers' actions always result in events that are consistent with the past. Retrocausality is a speculative concept in physics that suggests the possibility of causal influences travelling backward in time. While retrocausality remains a topic of theoretical investigation, it challenges our conventional understanding of causality and the arrow of time, raising questions about the fundamental nature of causation in the universe. Proposed mechanisms for retrocausality involve theoretical frameworks that allow for information or influences to travel backward in time, challenging the conventional arrow of time. One idea suggests that quantum entanglement could lead to retrocausal effects, where the measurement of one entangled particle instantaneously affects its counterpart, regardless of the distance between them in space and time. A tachyon is a hypothetical particle that travels faster than the speed of light. In theory, tachyons could possess imaginary mass and would always travel at speeds greater than the speed of light, making them impossible to slow down or stop. Properties of tachyons, if they exist, would include the ability to travel faster than the speed of light, violating the fundamental principles of special relativity. Tachyons would also exhibit unusual behaviour, such as backward causation, where their effects precede their causes. Causality violation refers to any scenario where the normal order of cause and effect is disrupted, leading to paradoxical or counterintuitive outcomes. Proposed mechanisms for causality violations include scenarios involving time travel, closed time-like curves, and exotic physical phenomena that challenge our understanding of causation. A cosmic string is a theoretical, one-dimensional topological defect in space-time, predicted by some models in theoretical physics. These cosmic strings are thought to have formed during the early moments of the universe and could potentially have observable effects on the large-scale structure of the cosmos. Properties of cosmic strings, if they exist, would include immense density and energy along a one-dimensional thread in space-time. Cosmic strings could generate gravitational waves and affect the distribution of matter in the universe, leaving behind observable signatures in astronomical observations. A domain wall is a hypothetical two-dimensional surface or boundary between regions of different energy states in a physical system. In cosmology, domain walls could have formed during phase transitions in the early universe and may contribute to the large-scale structure of the cosmos. Properties of domain walls would include a sharp boundary separating regions with distinct properties or energy densities. These walls could influence the evolution of the universe, affecting the distribution of matter and energy on cosmic scales. A monopole is a hypothetical elementary particle with a single magnetic pole, in contrast to the dipole structure of conventional magnets. Monopoles are predicted by some theories in particle physics and could have formed during the early universe. Properties of monopoles, if they exist, would include the presence of isolated magnetic charges, which would exert forces similar to electric charges. Monopoles could have profound implications for fundamental physics, including the unification of electromagnetic and weak nuclear forces. Topological defects are physical phenomena that arise due to the non-trivial topology of a system. These defects can manifest as localized deviations from the system's expected behavior and may have important implications for understanding the properties of materials and the evolution of the universe. Properties of topological defects depend on the specific system in which they occur, but often include localized changes in energy density or other physical quantities. Examples of topological defects include cosmic strings, domain walls, and monopoles, which arise in various contexts in theoretical physics and cosmology. A false vacuum is a metastable state of a quantum field that appears stable but is not the true lowest energy state of the system. In cosmology, false vacua play a role in theories of inflation, where the universe undergoes rapid expansion due to the energy associated with the false vacuum. A phase transition is a physical process in which a system transitions from one state to another, typically due to changes in temperature, pressure, or other external conditions. Examples of phase transitions include the solid to liquid transition and the liquid to gas transition. In cosmology, the phase transitions may have occurred during the early universe and could have left behind observable signatures in the cosmic microwave background radiation and the large-scale structure of the cosmos. Symmetry breaking is a concept in physics where the symmetry of a system is not preserved under certain conditions. For example, in a phase transition, the symmetry of the system may change, leading to new properties or behaviours. This can manifest as the breaking of rotational symmetry or translational symmetry, among others. Broken symmetries occur when a system's symmetry is not apparent in its lowest energy state. This often leads to the emergence of patterns or structures that were not present at high energies. In condensed matter physics, broken symmetries can give rise to phenomena like magnetic ordering or superconductivity. Spontaneous symmetry breaking occurs when a system's symmetry is broken without any external influence. Instead, the system transitions to a state of lower symmetry on its own, often due to subtle interactions between its components. This concept is essential in understanding the behaviour of physical systems, ranging from subatomic particles to cosmological phenomena. In the context of spontaneous symmetry breaking, properties such as order parameters emerge, which characterise the transition from a symmetric to a broken symmetry state. These order parameters describe the new properties or behaviours that arise as a result of the symmetry breaking, providing insight into the underlying physics of the system. The vacuum state in quantum field theory refers to the lowest energy state of a quantum field. It is often considered the empty state of the field, devoid of particles or excitations. However, even in this seemingly empty state, quantum fluctuations occur, giving rise to virtual particle, antiparticle pairs that continuously pop in and out of existence. Vacuum energy is the energy associated with the vacuum state of a quantum field. Despite being called vacuum energy, it is not directly observable as a source of energy in the traditional sense. However, vacuum energy plays a crucial role in various physical phenomena, including the accelerated expansion of the universe, as predicted by Einstein's cosmological constant. Vacuum fluctuations are temporary changes in the energy density of the vacuum state, arising from the inherent uncertainty in quantum mechanics. These fluctuations can give rise to observable effects, such as the Casimir effect, where two closely spaced conductive plates experience an attractive force due to quantum fluctuations in the vacuum between them. A quantum field is a mathematical construct used to describe the fundamental building blocks of nature, such as particles and forces within the framework of quantum mechanics. Each point in space and time is associated with a quantum field, which can fluctuate and interact with other fields to produce observable phenomena. Properties of quantum fields include quantization, where the field's values are discrete rather than continuous, and field excitations, which manifest as particles or quanta. Quantum fields also obey specific mathematical equations, such as the Schrödinger equation or the Dirac equation, which govern their behaviour and evolution. Quantum vacuums exhibit properties such as zero-point energy, where even in the absence of external influences, quantum fluctuations contribute a non-zero energy to the vacuum state. This zero-point energy has implications for phenomena such as the Casimir effect and the Lamb shift, where quantum fluctuations lead to observable effects in atomic and subatomic systems. Vacuum polarization is a phenomenon in quantum field theory, where virtual particle-antiparticle pairs in the vacuum state interact with external electric or magnetic fields, leading to polarization effects. This polarization modifies the properties of the vacuum affecting phenomena such as the electromagnetic interactions between charged particles and the behaviour of light in strong gravitational fields. As we conclude our exploration of physics, we hope you've gained a deeper understanding of the fundamental principles that govern the universe. Don't forget to subscribe to Loops and Loops for more enthralling content on physics, cosmology, and the wonders of the cosmos. Let's continue to embrace new knowledge, cultivate our curiosity, and deepen our appreciation for the physical laws that govern our existence. Until next time, ensure your loops are securely fastened. Continue your exploration and marvel at the captivating mysteries of physics. Thank you for joining us on this enlightening journey.